Welcome to The Explainer. Today, we're setting out on a quest, really, to get our heads around one of humanity's biggest, oldest ambitions, creating an artificial mind. We're going to trace the entire journey, starting with our only blueprint, the human brain, and follow it all the way to the generative AI that is, right now, changing everything.
So where do you even start with something that huge? Well, it all boils down to this one single question. And for centuries, this question has been the driving force behind scientists and philosophers, pushing them to try and, well, reverse engineer the most complex object in the known universe, our brain. Okay, before we even try to build a mind, we have to tackle a really fundamental question. Is there some essential difference between a natural system, say a bird, and an artificial one, like an airplane? The argument here is maybe not. When you get right down to it, both are just matter and energy. They're both governed by the exact same laws of physics. And if that's true, then building a mind suddenly stops being about some kind of magic and starts looking a lot more like an engineering problem.
Right, but calling it an engineering problem might just be the understatement of the century. The sheer, mind-boggling scale of the brain throws up a huge roadblock, something philosophers and scientists call the complexity objection.
You see, the human brain is the textbook example of a complex system. It's not just the parts themselves, it's how they interact. Incredible things, like consciousness itself, they don't live in any single neuron. They emerge from the interactions of billions of these tiny parts. So it's pretty clear. If we're ever going to have a shot at building an artificial mind, we've got to understand the original blueprint first.
So what is it that makes our brain so special? Let's pop the hood and look at the specs on this incredible biological machine.
First off, its efficiency is it's breathtaking. The entire human brain, everything it does, from reasoning to creating art to feeling love, it does all of that on just 20 watts of power. Yeah, that's about the same as a dim little light bulb. And what do you get for that tiny energy budget? You get this, an estimated 10 quadrillion synapses. That's a 10 with 15 zeros after it. These synapses, these are the connections between our neurons. They're the tiny, microscopic gaps where all the magic happens, where every single thought, every memory, every feeling is born.
And here's where it gets really cool. Those connections, they aren't fixed. Learning isn't some abstract idea. It is a physical process called synaptic plasticity. Every time you learn something, certain pathways in your brain get used. And the more you use them, the stronger those connections become. It's a process called long-term potentiation. So think about that. When you learn a new skill, you are literally physically rewiring your own brain. And that very process is the direct inspiration for how we train artificial neural networks today.
Okay, so armed with this amazing biological blueprint, the early AI pioneers set out on a truly monumental task, trying to translate the functions of the mind into the language of computers into code. The central idea they started with was actually pretty simple, but also really profound. It's this: what if thinking is just a kind of computation? This became known as the symbol system hypothesis. The thinking was, if you could just teach a machine to manipulate symbols based on a set of rules, you could, in theory, create genuine intelligence.
But this approach hit a wall, and it hit it hard. See, computers turned out to be amazing at well-defined problems, things with clear logical rules, like doing math or playing chess. But they completely failed at the messy, ill-defined problems that you and I solve every single second without even thinking. Like a taxi driver trying to navigate rush hour traffic. There's no single correct answer. It's just a constant stream of good enough, intuitive judgments.
So to try and crack that nut, researchers came up with what they called cognitive architectures. Think of them as different blueprints for how a mind could be built. You had some, like SOAR, that were based on a whole bunch of if-then rules. Then you had others, like the BDI framework, that tried to model an agent based on its beliefs, desires, and intentions. Each one was a different swing at trying to map the messy, unpredictable parts of how we think.
And for decades, AI research chugged along. Progress was steady, sure, but it felt incremental. That is, until a series of incredible breakthroughs, really just in the last decade or so, catapulted us into a completely new era, the generative revolution.
And you can just see on this timeline how fast things took off. I mean, we had early models, but 2017, with the introduction of the transformer architecture, that was the spark. In just a few short years, we went from GPT-3 generating really powerful text, to DALL-E making images out of thin air from a prompt, to GPT-4 handling multiple types of information at once. The pace here isn't just fast, it's exponential.
So what was the big breakthrough? It's a model called the transformer. And its superpower is a clever mechanism called self-attention. Now, instead of just reading a sentence one word at a time like older models, a transformer can look at the entire sentence at once. It can weigh the importance of every single word in relation to every other word. This is what finally cracked the code on understanding context, which was a massive, massive hurdle for every model that came before it.
And right around the same time, another brilliant idea popped up: Generative Adversarial Networks, or GANs. This is so clever. You basically pit two neural networks against each other. One is the generator. Think of it as an art forger, trying to create fakes that are totally indistinguishable from the real thing. The other is the discriminator, the detective whose only job is to spot the forgeries. They go back and forth, and in this constant competition, they both get ridiculously good, really, really fast.
And that brings us right up to today. This stuff isn't just a lab experiment anymore. The decades-long quest to build a mind has finally crashed into reality, and it is actively reshaping our world as we speak.
And you can already see its impact everywhere you look. Businesses are using generative AI to write their ad copy, to generate real estate descriptions, to power customer service chatbots that are actually helpful. It's being used to simulate complex supply chains, to automate boring business reports, even to help with scientific discovery. It's rapidly becoming this fundamental new layer of technology for almost every industry.
And this really gets to the heart of the immediate value here. Look at the difference. AI can take these tasks that used to require a ton of manual effort and just shrink the time it takes to do them. And for a lot of people, the goal here isn't to replace humans, but to augment them. To free us up from the repetitive grunt work so we can focus on the bigger picture, on strategy and creativity.
But, of course, with all this power comes some pretty significant challenges. This isn't easy. Training these models takes absolutely massive data sets and a staggering amount of computing power. And they can and do absorb and even amplify the biases that are hidden in all that training data. So now we're grappling with these enormous questions about ethics, about potential misuse, about fairness, about who owns what. And we're just at the very beginning of figuring out the answers. So that leaves us here, our centuries-long quest to build an artificial mind. Well, it seems to be succeeding, and at a pace that almost nobody predicted. But in achieving that goal, we've created a brand new, massive question for ourselves. What does our future look like as we learn to live and work alongside these new minds we've brought into the world? That's a story that's still being written, and we're all a part of it.